Hello everyone, I'm Janina Strobel from the University Hospital of Cologne. I'm very happy to present you today our little project. We developed a standardized method to calibrate multi-vendor MR-HIFU system used, for example, in clinical trials. So let me just briefly explain you the scope of this project. As we all know, there are many different MR-HIFU systems from different manufacturers on the market. So this led us to the question, how can we make treatment with those different systems using, for example, different transducers, different temperature monitoring systems? How can we make them comparable? This is very important for regulatory issues, for example, if you want to design a multi-center trial. So we decided to develop and characterize a bone phantom. Take a closer look at this bone phantom. We set ourselves some requirements. For example, it should produce, of course, reproducible results over time in independent measurements. This is obviously the most important aspect. It should also have a long shelf life, and we did not only produce a simple flat shape, but we also wanted to have individual bone shapes. Furthermore, the production of the phantom should be reproducible and give, again, consistent measurements. Our first step was to find a suitable material. We tried different materials such as the 3D printable synthetic resin Verovite and different polymers such as polycarbonate and PMMA. But they showed damages even at low power rates, as you can see in the pictures. So we needed to come up with another material which is more temperature resistant. This led us to the idea to use an ultrasound absorber made of polyurethane. It is very temperature resistant, mechanically stable, and as we saw in our experiments, it produces reproducible measurements. Now, to give you an overview of our workflow, we first created the phantom by casting polyacrylamide gel in a plastic container. First only a base layer, then we let it dry for 10 minutes. Afterwards, we put our flat absorber and casted another layer of this polyacrylamide gel until the plastic container was completely full. After that, we placed it on the HIFU tabletop with a customized positioning plate, so the phantom would always be in the same place. And then we started our specific treatment and did a data analysis via Python. Let me explain the data analysis a little more detailed. In the picture you can see a temperature distribution map with the brightest pixels being the hottest. Now what we did was we defined a region of interest, a ROI of the size of 4 mm by 10 mm, placed it 4 mm away from the surface of the absorber because directly inside or at the surface of the absorber there was no temperature measurement possible. And then we calculated the mean and maximum temperature difference in that specific ROI. Now let's jump to the results. Over a time period of 11 weeks, we performed 20 sonications on the same phantom. We used an 8 mm treatment cell, a sonication power of 40 watts and a duration of 20 seconds on a Sonali V2 MR-HIFU system. On the left side, you can see the mean temperature difference in our specific region of interest over the sonication time, and on the right side, you can see the maximum temperature difference in the same ROI over time. Both of the measurements were quite consistent and reproducible over time, and also the phantom did not show any signs of visible degradation. Another interesting outcome of our project was that this polyurethane material is not only limited to a simple flat shape, but we could also create individual shapes such as, for example, facet joints or femurs. We achieved this by segmentation of a CT scan, afterwards creating and 3D printing of a mold. This mold could afterwards be filled with the liquid polyurethane. The mold had to be removed, and then the phantom is ready for, again, treatment with different protocols. So to sum it all up, our polyurethane polymeric material is temperature resistant with high ultrasound absorbance. We had reproducible measurements over a period of several months, so the absorber can be used as a bone phantom for quality assurance. One limitation of the study is that the measurements have only been conducted on a sonar leaf system so far, but in the future we would like to try them also on other systems. Regarding the phantoms made of cast polyurethane, this is a feasible way to test sonication protocols, and in the future it could be used for regulatory issues and also as a training for doctors. In the end, I hope you enjoyed these presentations. If you have any questions, feel free to ask them in the chat.